Right. Welcome, everyone. My name's Kai, and I am a grad student in the UNZ Research Group at University of California, San Diego, and I will be introducing today's speaker. But before we get started, I just want to remind you that we have a Facebook page called Polariton Chemistry Online Community. Here we post updates about upcoming webinars, and we also encourage the sharing and discussion of scientific publications amongst the members of the community. We also have a YouTube channel. Here we post recordings of the webinars. Please subscribe. Here you can watch a webinar that you missed, or if you just want to rewatch your favorite webinar. And then briefly, I just want to go over again the mechanics of the webinar for attendee participation. So to ask an oral question, please use the raise hand option at the bottom of your screen. When you do, I will notify the speaker, and then I will enable your mic so you can personally ask your question. If you want to submit a written question, please use the Q&A option at the bottom of your screen. And due to the interest of time, these questions will be answered at the end of the webinar. And with that, it is my honor to introduce today's speaker, Professor Marina Litinskaya from the University of British Columbia. Dr. Litinskaya received her PhD from Scuola Normale Superiore, studying the optics of nanostructures. She was a postdoctoral fellow at the Université de Strasbourg, was a senior researcher at the Institute for Spectroscopy, Russian Academy of Sciences, and was a Humboldt Research Fellow at Ulm University. Her research interests include atomic, molecular, and optical physics in conjunction with condensed matter systems. And today she'll be talking about the merging of these two areas of research. And with that, join me from wherever you are, giving a warm welcome to Professor Litinskaya. The screen is yours.
Thank you. Thank you for this introduction, Kai, and thank you for inviting me. I'll try to share my screen at this point. Yeah, can you see that?
Yeah, we can see the screen.
Thank you. So, thank you very much for inviting me. My story is here. I was working on polaritons and nanostructures, and at some point at a conference, I came to a wrong section and realized that I don't want to leave. And it was atomic and molecular section. And what was very astounding about this section is that it seemed like people there had a magic wand. So if something did not work in the system, they would just fine-tune a couple of parameters, and here they go, and everything works, and they have what they want. And so I started to drift slowly towards atomic and molecular optics. And so as many other people did. And so this first line in my title, Merging Condensed Matter Physics and AMO, it's basically a huge effort which done by many people. So I'm not going to review the whole area today, but instead I would like to talk about three works on my personal phase trajectory, which in my opinion have a common denominator. They illustrate how a concept from one field benefits when it is transferred to another field. Okay, so this is the idea of this talk. The introduction to the first part of my talk, so it consists of three parts. The introduction to the first part in large strokes is here. So we know a lot about solid crystals, right? We know about quasiparticles that live in the air, etc. So we have some knowledge. What people do in AMO, in atomic and molecular optics, then can produce these crystals in air. So they have two controllable propagating lasers. Two, if they want to have a one-dimensional crystal, four, if they want to have two-dimensional, or six, if they think about the three-dimensional crystals, and they build basically these crystals in air. They create potentials which trap particles, one particle per lattice site. It can be an atom, it can be a molecule. And so you have a crystal, and the parameters of the particles in these crystals are highly tunable. And now the question is, what will happen if we will take some quasi-particles from solid state crystal and transfer them into this new soil? The difference here is, the difference between these two objects is that here the lattice constant is about 400 nanometers as opposed to, say, 5 angstroms here. And so it allows you to address all the sites individually by electric field, for example. And in addition to that, if you apply an external perturbation such as electric field, it can vary considerably from one lattice site to another. So this is the major difference, and let's see where it can bring us. Okay, so the first part of my talk is about rotational Frenkel excitons in optical lattices. Let me remind you about Frenkel excitons in molecular crystals. So what is the quasiparticle which I'm going to transfer to the optical lattice? So it's Frenkel exciton, not a Van Yemot, but a Frenkel exciton. We have a molecular crystal, so basically a lattice of two-level systems. Ground state, excited state. This is the excitation energy. The ground state is when, of course, everybody is in the ground state, and the first excited state is just one molecule is excited. We assume that the excitation can hop from one molecule to another via dipole-dipole interaction, and the nearest neighbor hopping constant would be J, and so hopping to the next site would be J over 8, since the distance doubles, etc. So the excitation can propagate throughout the crystal lattice. So if there is no interaction, then the eigenstates of the crystal would be just the excitations of individual molecules. If you allow for the excitation transfer, then this excitation would kind of leak out of this molecule and will be equivalently distributed among all the molecules of this chain. So this is the Hamiltonian, which includes excitations of each lattice and excitation transfer via dipole-dipole interaction. And this would be the wave function. So this new quasiparticle, the eigenstate of this Hamiltonian with dipole-dipole interaction, is what is called Frenkel exciton. Each molecule has a probability of 1 over n to be excited, right? And each molecule has such a phase factor. And k is the wave vector of the exciton. And it's how the energy of the exciton looks like in k space. In the nearest neighbor approximation, it is just a cosine. So j in cosine k times a. Yeah? So these are the eigenstates of the Hamiltonian, known as Frenkel excitons since 1931. Now let's see how this particle will behave in an optical lattice and what we can do with it. So, first of all, instead of electronic excitations, which I discussed at the previous slide, in crystals we typically deal with electronic excitations. Now we have, say, lithium-cesium molecules placed one per lattice site in an optical lattice, in one-dimensional maybe. Why lithium-cesium? Because these are polar molecules, they interact strongly with each other, they interact nicely with the electric field, right? And again, we assume low excitation limit, just one excitation is shared by all the molecules. Instead of the electronic transitions, we consider first rotation excitation. So from n equal to 0 to n equal to 1, and m is always equal to 0. This is the Hamiltonian, and we include some electric field. We basically want to add electric field to to shift m equal to 0 level from m equal to plus minus 1. So we have just a separate transition, and it will be our rotational Frenkel exciton. And you can get exactly the same picture as in crystals. So this is these are the dispersion curve. The first bonus that we have, and these are the parameters. The parameters are, of course, different because we are dealing with a rotational excitation and not the electronic transition. But the first bonus that we have is that, for example, changing the direction of the electric field, we can modify the hopping parameter, the dipole-dipole interaction between the molecules. So we can change, for example, here you see that the effective mass of the Frenkel exciton is positive. Here it is negative. We can suppress the excitation transfer just by changing the direction of this external electric field. So we are not going to use this. It's just to start with. And what we are going to do, so we have these excitations that are similar to solid state excitations. What we can do with them? So this is the excitonic wave function. If it is just a plain wave state, then these factors are the exponents with a wave vector. If it is an excitonic wave packet, they are just something else, right? We can create wave packets of excitons. And what will happen to this exciton if we come up with some perturbation, maybe with some electric field? And to answer this question, let's recall about the Adiabatic theorem. Assume that we have a slow perturbation. So some perturbation is switched on, and after some time, it goes out. So if the perturbation is slow, you can characterize your system by instantaneous energies, right? Slow with respect to the distance between the energy levels of your system. So this is the instantaneous energy. That's how it behaves, for example. And you know that after the perturbation is over, your system will be described by a state the same as before, and also carrying an extra phase factor. So basically, the slow perturbation imposes a phase on each state in your system. And this phase can be calculated as an integral over this instantaneous energy state. So if we come with an external electric field, we have a bunch of levels. Each molecule has a ground state and an excited state. Each of them picks up a phase, right? And it is easy to convince yourself that the excitonic wave function after the slow perturbation is over, each monomer, each two-level system picks up a phase, such a phase which looks like this, and it depends on the location, because it depends on what the electric field at the location of this specific molecule is. So we can change the phases of individual molecules. And this is what is called phase kick. By an external perturbation, by an external electric field, we can implement a site-dependent phase imparted on the excitonic wave function, and the details of this phase will depend on the perturbation. So basically, we need to come up with some perturbation which would affect the dynamics of the energy levels in such a way that it produces a phase that we want. Now, the important thing is that we should have, what is the duration of this perturbation? As I said, the perturbation should be slow with respect to 1 over excitation energy, right? Because we don't want to have a population transfer. We don't want to excite these molecules, but it should be sudden with respect to the scale 1 over j to the excitation transfer, because we want to impart the phase onto specific exciton. We don't want that the excitonic state, so that the excitation transfers during the time in which we impose this phase. So this is the basic idea. Site-dependent phase can be implemented on the excitonic wave function. And let's see what we can do with that. Okay, let's see what we can do with this phase. So, fact number one, that is what we called phase kicks or momentum kicks. So this is the idea which we are going to explore. This is the excitonic function after the perturbation. Each monomer, each excited monomer acquires a phase as specified by the details of that perturbation at the location of this particle. So if we look at the excitonic state, remember, if an exciton is a plane wave, then these coefficients look like this. So basically it's 1 over square root of n, and then e to the power of I, k, a, n. So basically, they have the same amplitude and they have phases that linearly depend on the coordinate. N is the side number, right? So wave vector, each wave vector state is basically a linear phase which is distributed among the molecules, which tells us that if we can impart such a phase, impose such a phase, which will be linear in the coordinate, which we can write down as f naught plus n a times delta. It means that an exciton with a wave vector k will become an exciton with the wave vector k plus delta. So if we can come up with the electric field that induces such a dynamics of the molecular levels that the imparted phase is linear in the coordinate, we'll just increase the excitonic momentum by a certain amount, right? So we can manipulate the momentum of the excitons. I will be talking on a very qualitative level, but in fact, in our publication, we came up with the specific parameters with a laser beam which can impart such a linear phase transformation. So here, just the idea. Okay, so what this can be good for? So assume that we have some excitonic wave packet. So if it is just one exciton with a wave vector k, we add momentum delta. If it is a wave packet made of several k states, then we add momentum delta to each of these k states. What it can be good for? Well, for example, let's consider an excitonic wave packet which is sitting here at around k equal to 0. And assume we give it a phase kick, and now, when it is sitting here, first of all, it does not propagate. You see that the group velocity here is close to 0, so it sits still, and also it spreads because quasiparticles with quadratic dispersion spread during the time evolution. Now we give it a phase kick, say to the middle of the brilliant zone, and now it is here. Here the dispersion is linear. So it propagates, its group velocity is non-zero, it starts propagating, right? And also, due to the fact that the dispersion is linear, it does not spread. So it propagates with preserving its shape. So what we can do by this phase transformation, we can modify the group velocity of the wave packet. We can accelerate them and decelerate them by bringing them back to the bottom of the brilliant zone. We can protect them from spreading when we put them here at the linear part of the spectrum. We also can protect them from radiative decay, because these states decay radiatively while these do not. So we can manipulate the dynamics of the wave packet. And here, this is the simulation of this process. So you see we had this relatively narrow wave packet. This is the side index. It was a wave packet sitting in the middle of the lattice. And then we introduced this phase kick with the help of a laser beam, right? So we added a equal to minus pi over 2 at a time scale of 3 microseconds. And you see how the phase develops during this phase kick. And after that, the wave packet starts propagating because now it is here in the middle of the brilliant zone. It has finite speed and it propagates, and you see that it indeed does not spread. So this is the numerical implementation of this momentum kick of the excitonic wave packet. This was thing number one that we can do with the excitons. And thing number two is focusing. So assume that we have a broad excitonic wave packet and we want to localize it on a specific lattice site. What would be a phase transformation that would do the job? It would be a quadratic phase. By analogy with optics, we know that a lens, a focusing lens, is a quadratic phase transformation, right? So let's try this thing. And again, in our paper, we came up with the parameters of the, again, Gaussian laser beam that can impart such a phase onto all the monomers. So what will happen this time? Yeah, there is some peculiarity in this problem. The point is that we want to focus a broad wave packet, right? This broad wave packet consists of some k states. And it turns out that the waves in the quadratic part of the spectrum, they obey this focusing all right. And the waves from the linear part of the spectrum, they resist focusing, they just propagate as they are. So what for the parameter phi naught do we need here? On one hand, it should be large because the larger the amplitude of this phase, this phi naught constant, the larger the effect of the focusing. On the other hand, it should be not too large because we don't want the components of this wave packet to be kicked out into the region where the dispersion becomes linear. So we can calculate the optimal phase strength phi naught, which would work for a specific wave packet with certain width. Then this would be the time within which it focuses, and basically you can see that it can focus at an area at a region of the order of one lattice site. And this is again the simulation. So we started with focusing a plane wave. This is a plane wave. And we apply such a quadratic phase transformation with n not equal to this site here. And you see that a plane wave in time t star focuses at a size close to one lattice site. This is the focusing of a broad Gaussian wave packet. So this was our initial distribution of the exciton wave packet on the sites, right? It's spatial distribution of the excitonic wave packet. And now you can focus it to a small size. You can do the same thing in 2 dimensions. Again, you impose a quadratic phase transformation and you can focus such a broad wave packet. And we demonstrate here that we can localize it anywhere on demand. You just choose the site coordinates nx0 and ny0 here, and you focus your excitonic wave packet here, or here, or here. And again, everything is done by a laser beam. The phase is imparted by the laser beam. Now, real structures are disordered. We checked that the scheme can survive at least 10% of vacancies. So this is a lattice with 10% of lattice site empty. This is the initial excitonic wave packet, and that's how it is localized by such a quadratic phase kick, phase transformation. Here you can see what you would have if just the state, if you let the state propagate on its own, because there will be some dynamics in this disordered potential, right? So it will find some minima in which it will settle down. So this would be the dynamics without phase kicks. And this what we can do with our phase kit if we want to put this excitation onto this molecule. It's not ideal, but it's pretty good. Okay. Actually, real optical lattices with polar molecules, they are not good enough. So we demonstrated that, in fact, this scheme can be used also in a highly disordered medium, but some modification is required. So this is an optical lattice with 60% of vacancies. So only 40% of molecules are in there. It's a strongly disordered system above the percolation threshold. But still, you see that you can focus your excitation on one lattice site. To do that, you need to apply a matrix. Well, the fast transformation in this case looks somewhat differently. You basically split your lattice into small squares. And to each square, you apply a specific phase. And you apply them in such a way that the signals from all these small squares come to this point in such a way that they interfere constructively. Then this results in the enhanced magnitude of the signal at this point. Okay, so basically, this is one thing that you can do with excitons in an optical lattice, which you can't do in solids, because here you can address the molecules individually. It's not the only thing that you can do. There are many other nice tricks that you can do with excitons in optical lattice. For example, you can have not only vacancies, right? You can have impurities. You can replace one lithium cesium molecule by something else, maybe by lithium rubidium, right? And then this molecule would have a different excitation energy. And this difference in the excitation energy between lithium rubidium and the host molecules would act as a scattering potential, which scatters exciton. And the interesting thing is that you can tune this difference by applying the external electric field, so that you can switch this potential on and off. And so you can induce transition from a localized state to delocalized state and back to a localized state, just by tuning this scattering potential. Another thing that you can do with excitons in optical lattices is here. Basically, you can create biexcitons. It is bound states of two excitons. So you have two excitons and you bind them together, forming a biexciton state. And you can associate and dissociate these biexcitons just by changing the magnitude of the applied electric field. So this slide actually summarizes that excitons in optical lattices is a beautiful platform. There is a whole zoo of various controllable elements. You can speed them up, you can slow them down, you can localize them on lattice side, you can delocalize them over the whole lattice, you can bind them together, you can control their shape. So it's a beautiful platform for something like, I don't know, quantum memory, gates, whatever. My personal perspective of this, my personal conclusion is that optical lattice is probably not the ideal platform for this rotational excitons, for this controllable excitons, because according to what I know, so far we are not close to filling factors close to 1, and there are technical difficulties to produce these factors. So these optical lattices are still highly disordered, but maybe this set of ideas can be transferred to yet another platform, because basically all what you need to do all this is a set of two-level systems that interact strongly with each other and that are controllable by the external field in such a way that this field varies at a considerable scale from monomer to monomer, and that's it. And then you can have all these elements. So this was the first part of my talk. And let me now switch the subject and talk about something different. It's the second idea which we were trying to replant from condensed matter to optics of gases. It's about negative refraction and photonic crystal optics in optical lattices. To start with, let me tell you about negative refraction, a few words about negative refraction. So we all know how light refracts at a boundary between two media. So this is air, this is a material, this is a coming light, and this is how it is refracted, right? And this obeys Snell's law written here. However, if you look at it closely, there is a second wave, this one, which also obeys the Snell law. Why do we typically neglect this wave? Well, because it looks like it doesn't conserve energy, right? So it looks like this, it doesn't satisfy boundary conditions. It looks like this wave carries the energy from infinity to the interface. So we just disregard this solution. However, there is a class of waves, basically the waves with negative group velocity, for which the direction of the energy propagation, the group velocity, and the direction of the wave vector are opposite. So if you have a wave with negative group velocity or with the decreasing slope of the dispersion curve, it's the same, then in fact, you should pick this solution and not this one, because it will be the solution which satisfies the boundary condition. And this is what is called negative refraction. Incident light, refracted light. A few words about what negative refraction is good for, how the world with negative refraction would look like. So you can look around the corners. Here, you don't see this fish, right? Because this is how the ray go. And if the liquid was negatively refracting, you would see this fish, right? Another famous example is Vesilaga's lens. We all know that a planar slab does not focus light because that's how the rays would go through a planar slab of some material. However, if the material was negatively refracting, it would act as a lens. And this lens basically focuses on subdiffraction limit, as Pendry showed. So other examples of negative refraction include superprism, like shown here, invisibility cloak based on negative refraction, if you look at how the rays go, illusion optics, because the way the rays go in an unusual way, you basically can create optical illusions and substitute one object with a vision of a different object. So the whole bunch of phenomena, right? And we thought that it would be very good to implement this in gas. So you have your laser, you switch it on, and you have your invisibility cloak, tunable at a distance in real time, right? It would be nice. Now, what about the gas? Before talking about gas, let's talk about solids, because why we don't know why it sounds so unusual, so counterintuitive, because we never can observe negative refraction in our everyday life. And it happens because it looks like nature resists negative refraction in many different ways. For example, as I said, any wave with negative group velocity would negatively refract. And we know from condensed matter that there are waves with a negative slope of the dispersion curves. For example, these are the polaritons with an exciton with a negative effective mass, right? So this was the negative slope of the exciton, and these are the polaritons. And here you have a negatively refracting wave. These are the eigenmodes in a giratropic crystal. This is a negatively refracting wave. So negative group velocity, negatively refracting mode, and same here. So we do have waves with negative group velocity in conventional solids. What is the problem here? You see that for all these waves with who refract negatively, we have a resonant wave which refracts positively. And this wave is much more natural. So if this is the light line. So this would be the light line. So this is, here you would have the exciton, right? Here you would have an exciton, and here you would have the light line in this polariton. And you see that this light line is very close to the positive wave and very far away in the phase space from the negative wave. So basically, the incoming light talks to the positive wave and does not talk too much to the negatively refracting mode. So the overwhelming majority of incoming light goes into the positively refracting mode, and the negatively refracting mode can be barely seen on top of this. Next, another important point is that in all these examples, typically the width of the negatively refraction window, the part of the dispersion curve where you have negative refraction, is small compared to losses. So typically losses beat negative refraction in these materials. What else can we have? Okay, we can have overlapping epsilon and mu resonances. So if this is the dielectric function, this is the magnetic response, if the resonances would be close, that would have been the modes in the system. And here you can see a wave with a negative group velocity, negatively refracting mode, which does not have a positive counterpart, positively refracting counterpart. Unfortunately, there are no natural materials with overlapping epsilon and mu resonances. And this is the whole story about metamaterials, where people try to create successfully and demonstrate negative refraction. Artificial materials with overlapping epsilon and mu resonances. But in nature, there are no such materials. In principle, this picture looks similar to surface plasmons, right? So there is a surface plasmon with a similar dispersion. This line would go here. And indeed, negative refraction was demonstrated for surface plasmons in 2007, I think. Aside from that, there are no suitable natural materials. If we start thinking about a gas, because we want to realize this phenomenon in a gas, things even get worse because, first of all, gas has a low density, and hence it interacts weaker with light, with external light. And you cannot increase the density of gas infinitely, because it will eventually become a solid. Next, in order to have visible response from the gas, you need to work near a resonance, and it means high absorption. So everything will be absorbed, and that's why gases are tricky. The best, to my taste, proposal in a gas was 3 orders of magnitude away for the density from what is available in the labs. So, since there are no natural materials which would provide us with a properly negatively refracting mode, we decided to look at a different route to the negative refraction. We decided to adopt the approach from photonic crystal optics. So that's how it works in photonic crystals. Assume that this is a photonic crystal, so it's a layer of material with alternating slabs of some material vacuum, and this is an incident photon. If you look at the eigenmodes that exist in this crystal, you will see that there are 2 types of modes. They are wave packet. These are the amplitudes. There are wave packets created like this. So this is the common factor. Kx is the wave number along along x-axis into the crystal. So this thing propagates as a whole into the crystal, and this is described by kx. And in kz, k parallel, you have this translational symmetry. So kz is the same for the incident photon for all these modes, but due to periodicity, there are different harmonics, 1, 2, 3, etc. And they differ by integer number of 2 pi over a lattice constants wave vectors. And at certain angles of incidence, you can have two such wave packets, one negatively refracting, one positively refracting, as shown here. We can look at this picture in the phase space. So this is so kx, kz, the two wave vectors, and the black line. So this is the incident photon. It's an equi-frequency surface. This is the dispersion of the incident photon, right? And this would be just the black line. This long black line is the equi-frequency surface for the modes inside this crystal. So they would have been the circles, right, for each of the components, but these components are coupled through the lattice, and so the small gaps open here. And if you come up with a certain external photon with some kz, it excites the modes with the same kz, and this would be the positive wave packet, which you can see here, and this would be the negative wave packet, which you can see here. And indeed, you see that they propagate in two different directions. This one is positively refracted, this one is negatively refracted. So that's how it is described in the K-space, if it helps. Now, and now the idea is, okay, so this is what we know about the photonic crystals, and now let's just replace this materials by atoms, with atoms in a one-dimensional optical lattice. So you can have the so-called pancake optical lattice. You have two laser beams which create layers of atoms, and so each material layer is replaced by a layer of atoms hanging in the air, and then we'll do the same thing as shown here. Why not? That's why. The problem is that the main concern here is that in principle we can never hit the negatively refracting mode because we do not have a proper interface between the gas and the vacuum from where the photon comes. So the problem is that, again, this adiabatic theorem. So if you have a time-dependent Hamiltonian and you have these instantaneous energies as function of time, so if your evolution is slow, that's what we know from adiabatic theorem, if your evolution is slow, then you will always stay within one and the same mode and will never jump to a different branch, right? If your evolution is slow. And here, the spatial profile development is very slow because there is no distinct boundary. And the external photon is positively refracting. So it will adiabatically connect to a positively refracting mode in the gas, and probably it will never jump onto a negatively refracting branch. So in principle, we do need to have some non-adiabaticity here in order to provide the population transfer into the negatively refracting mode. And that's how this is our spatial analog to the temporal evolution in the classical adiabatic theorem. Here we have slowly spatially changing gas boundary, and these are our eigenstates, the vectors of the positively and negatively refracting mode. So what can we do to hit that mode? What can we do? Yeah, and also again, in order to have large modulation, large profile, right, of our photonic crystal hanging in the air, we need to be close to the resonance, and it will mean increased absorption. So what would be the impact of this thing? Okay, to address the question about the boundary, we basically derived an optical analog of the adiabatic theorem. So this is what we have in quantum mechanics, and that's what we did for optics. The dynamics is described by the Schrödinger equation. Instead, we have Maxwell equations with a varying x-varying coordinate-dependent gas profile. The bases are the wave functions. Here we have our wave packets, negatively and positively refracting wave packets, these monsters. And this is the adiabatic condition for quantum mechanics, and that's what we have derived for our system. And basically we introduced the adiabaticity parameter, which tells you how large or small, how small your region within which the gas cloud develops should be. It depends on the distance between the modes. Again, in order to get transfer between the modes, this parameter larger than 1 means transfer between the modes, means populating the negatively refracting mode that we want. So L star should be relatively small. And here are the results. Here are the results. So this is something we are really proud of. This is the density which is available in the lab. So our proposal works for the densities available in the majority of the labs. This is the size of the entrance and exit region, about 20 microns, which also works. So in a relatively wide angular range, we can produce a population of the N mode, its amplitude, ranging between 0, 0.1 and 0.1, which is not too much, but it's okay. We remember that negatively refracting mode is always less populated than the positively refracting mode because it is less natural. And this is also a very good thing about this proposal, right? Because this is the frequency range up to, you can get this magnitude of the negatively refracting mode in the frequency window about 20 gammas, 20 absorption widths, which is much more than what we typically have in solids. And now let's look at the simulated wave propagation. So we derived a set of differential equations, slow varying amplitudes, coupled mode formalism, and then we solved the resulting equations numerically. And here is the result. Assume that we are at the detunic 7 gamma away from the resonance. So epsilon is not huge. This is the incoming photon positively refracting. It propagates through the crystal, indeed through the optical lattice. Indeed, you see that it has, well, the overwhelming majority of light is sitting here in the positively refracting mode, but you see creation of 2 negatively refracting beams. One is here and the second is here. And you can see that indeed this mode is pumped. The transfer into this mode happens at the entrance region and at the exit region, where the states come close together and transfer becomes positive. So basically this second beam and the fact that they appear here tells us that it's not a reflection, it's mode transfer into adiabatic mode, non-adiabatic population transfer into the negatively refracting mode. The interesting thing happens when we come closer to the resonance. Now we are at 3 gammas away from the resonance, and you see that the negatively refracting mode is still there, but the positively refracting mode gets depleted. It is absorbed by the lattice. If you look at the amplitude, you see that it gets absorbed. The negatively refracting mode is not. It is absorbed a little bit, but not much. While this one is practically absorbed. And when we come even closer, then that's what we see. The positively refracting mode is absorbed, but negatively refracting mode survives. So this is a unique situation when we eliminate the positively refracting mode and are left with the negatively refracted mode only. What's going on? Why positively refracted mode disappears, as you can see here, and negatively refracted mode is protected against absorption? And the answer is here on the next slide. So remember, we had this picture, these are the amplitudes. Let's look into these wave packets, into how they are constructed. So remember that each wave packet consists of harmonics. And if you look into the magnitudes of these harmonics, you will see that basically there are two dominant components in each wave packet and all the other contributions are small. So let's look into these dominant components. And you will see that the negatively refracting mode is asymmetric, while positively refracting mode is symmetric. And this is actually the key to what's going on here. Because if you translate this equality into human language, that's what you will see. Basically, you will see that this is the optical lattice, right? You will see that positively refracting mode has its nodes in the vacuum and its maxima in the atomic layers. And that's why it gets absorbed when you come closer to the resonance. In contrast, the negatively refracting mode has its antinodes in vacuum and zeros inside the material levels. And that is why it is resistant to the absorption. So basically, this part demonstrates that we can get that in optical lattices, we can get negative refraction in a gas with the parameters that are available in labs abundantly, and with the stabilization of the N mode and with the absorption of the positively refracting mode, the phenomenon about solid state analogs of which I am not aware of. I see that that we are approaching to the end of the seminar. I have also a third story in this series about optical nonlinearities for weak fields, and it's an example of a concept transfer from atomic and molecular optics to condensed matter, but I don't think that we can squeeze it into the remaining.
I have a quick question, actually. I have a question about the adiabatic theorem. So I'm trying to think about it in the sense of like the Born-Oppenheimer approximation, where the nuclei are slow, electrons are fast, and your surfaces are parameterized by the slow coordinate of the nuclei. I'm guessing I'm still a little confused. What is slow and fast in this in the gas system we're using for the negative refractivity?
What is slow and fast?
Mm-hmm. What's this? There's in when you think about molecular dynamics, the slow is the nuclei and the fast is the electron, and that's how you form it.
Thanks for raising this point. I did not tell that for that part we are not using molecules. In that optical lattice, we just have atoms. It's an atomic layer which interacts with light. So fast and slow, it means just in comparison with the distance between different layers. It is not related, like if you look here. So the adiabaticity condition for classical adiabatic theorem in quantum mechanics. The evolution should be slow as compared to the distance between the energy levels of your system, instantaneous energy levels. Only in this sense. Nothing going on inside the particles that that are in the lattice matters. So I think that probably I should drop the third part.
Okay, so the slow varying seems to be, I guess I'm not saying the slow varyings actually happen in molecules, but what's the analogous slow variable in your system, I guess? And I think the last picture seems to be the gas boundary, I guess? No, or density?
Here. So in my yeah, in my case, slow or fast means the distance. So these are the eigenmodes, my eigenmodes. This is the wave vector of the negatively refracting mode. This is the wave vector of the positively refracting mode. In order in order the population transfer to be efficient, they should be close in the phase space. So if we go back to this picture, you see here we have a positively refracting photon which populates this mode, but it is close in, when they are close in the phase space, then exchange between them is possible. This is, by the way, tells you why we don't have the reflected beams. If you have a solid boundary, if you have a well-defined boundary, you will also have a reflected wave packets, right? But here, the reflected wave packets are far away in the phase space, so they are never populated. So what matters here is the distance between the modes in the phase space in comparison to some parameters of the problem, basically as we have shown here. So this is the matrix element of the our Maxwell equation operator over the eigenstates of the system. And the distance between the modes should be small as compared to this matrix element.
Okay, thank you.
Yeah, it's similar like what we have here.
Okay, I see now. Great.
So I can either rush through the last part, but I don't think that it will be.
I want to see, at least open the floor for some questions. So if you have anyone in the audience that has a question.
Then maybe I can finish my talk.
Well, we have a few questions right now, so go ahead, Joel.
Sorry, I want to follow up on Kai's question. I'm still confused about when you say, okay, you are trying to populate the negative refraction mode, but it needs to be close in phase space to the positive refraction mode. Can you comment again? What is the adiabatic modulation? What is the degree of freedom that you're adiabatically modulating? I'm a bit confused about that also, which is, I think, the same question as Kai.
Okay, if I understood your question correctly. So in the case of classical adiabatic theorem, we have temporal dynamics, right? Yes. So it depends on how your Hamiltonian changes in time. Yes. Here we have spatial variation of the gas boundary. So instead of time, we have x, the coordinate.
Wait, but okay, no, yeah, you have x, and then what is the analog of energy in that case?
K states, the wave vectors of my modes. They are my quantum numbers.
Okay. So, okay, so the K, wait, but I'm a bit confused, but so you are saying at every X coordinate, you have different K values.
Exactly.
Okay, so you don't have a periodic system. So you have like you have a homogeneous system.
Exactly. Let me show you this picture. So this is zero. That's the beginning of the Anton zone. So here, this is basically the air, right? And here, I have my optical lattice. This is the region of maximum density, where Kp and Kn have certain values. And this is the entrance region, and this is the exit region, where we have this poorly defined boundary, where the gas density develops from 0 to 1. And that's how my eigenmodes Kp and Kn behave. Initially, they are close. And then the distance between them develops until it reaches the maximum distance that you have seen on that phase diagram.
So then the way I should think about this is, so there's a spatial distribution of atoms, but then this spatial distribution is also changing its periodicity in space adiabatically.
Yeah, basically, if we go here, so here you have the layers, the optical lattices here. The layers of atom are here, but they do not start sharp.
Okay, but this in principle could be also done with periodic this idea comes from metamaterials, I guess. So it also can be done just with regular slabs. I mean, is your strategy drawn from other types of strategies that are already used in metamaterials, or is this like something very specific for atomic gases?
In photonic crystals. This is called photonic crystals, and indeed there is a series of work about negative diffraction in photonic crystals, and they exactly explore this, which was this picture comes from this paper, and already on this picture you can see that at certain angles, if your photon comes with a wave vector from this region, right? Mm-hmm. So that it can excite a mode pointing here and a mode pointing here, then your external photon will excite a negatively refracting wave vector. Yeah, we based our work on this, but in a solid state, you cannot eliminate the positively refracting mode. You don't have absorption.
In the solid state, what? Sorry, can you repeat the last statement?
In the solid state realization in photonic crystals, you cannot eliminate the positively refracting mode.
Why is that?
You don't have absorption. You don't have absorption. It's just a layer of the material with a different dielectric constant, right? So maybe.
Well, but if you have like resonant media, you can, right?
Then maybe yes.
Okay.
But typically, people just have a layer of it's a contrast of the dielectric profile.
Okay, and very quickly, you said you were talking about filling fraction of optical lattices. Is this number of is this atoms per lattice site?
No. We always assume that we have one molecule per lattice site.
Filling fraction means?
Yeah, filling factor. It's the ratio of how many impurity, how many vacancies do you have? So with atoms, you can reach 99% fidelity. So basically a perfect crystal with one atom per lattice site. With optical lattices, as far as I know, we are still at about just 30%. So 70% are vacancies and 30, because it's difficult. It's a whole fabrication process. You basically put two species into the lattice, then you form the molecules inside the lattice, and then you transfer them to the low vibrational ground state.
So you say only 30% of those lattice sites are occupied by molecules.
Yeah, so it's above the percolation threshold, but not very good for the implementation of coherent excitations.
But why can you not just do the same thing just with atomic optical lattices?
You need dipole-dipole interaction, strong dipole interaction. People do something like this with magnetic atoms, and as I said, I do think that this bunch of ideas can nicely fit some realization.
Okay, thank you very much. That was very interesting.
You're very welcome. I'm very sorry. I see that I don't have time for the last part of my talk. So let me just show the last slide. I can just say that the last part was about putting the concepts from here back into condensed matter system. And in our recent work, we found a possibility to create an optical nonlinearity for weak fields, for arbitrarily weak fields, in spite of disorder that is present here. And well, maybe when we finish our paper, which we're working on now, probably we can submit it to the community instead of going over time. So I'll just skip this discussion, but I would like still to show my last slide. Yeah, this work was done with Felipe Herrera, who presented at the previous webinar. I would like to thank the people with whom I worked on these problems. So this is Evgeny Shapiro, my friend and colleague, who basically came up with the idea of the phase kicks and with whom we worked on negative refraction. These two people are Roman Krebs and Ping Xiang, with whom we worked on rotational excitons, and Ping basically did all the numerical simulations of the wave vector propagation that you have seen. And this person here is Felipe Herrera. He's now solving a complicated scattering problem, and we worked together on the third part, which I did not have time to present, and he was also involved in the rotational exciton thing. So at this point, I feel free to finish, and I will be happy to take other questions if they are there.
Yeah, we have a couple more questions.
Yes.
Go ahead, Matt.
Okay, I have a question about the second part of your talk. So you presented a way to transfer, energy from the positive refractive modes to the negative refractive modes, and even reduce the amplitude, right, of the positive refracting modes.
Yep.
And so and that strategy involved, changing the refractive index, right, of the material, right? So I was wondering if if instead of atomic lattice, you can use some working substance such that due to bath modes, there can be dissipative coupling between positive and negative refractive modes.
Well, you definitely can use other materials, as people do in photonic crystals. So you're basically saying a different realization where these layers will be absorptive, and they will absorb positively refracting mode and won't absorb negatively refracting mode, right?
Oh, no. So I mean, like, what if there were some bathed phonons, for example, that could mediate energy transfer between positive and refractive modes?
Maybe, but you need to find phonons which would transfer energy from positive to negative, but not the other way around, right? And according to what we have seen so far, nature indeed resists negative refraction in all possible ways. And so my first guess would be, if you find such a phonon, it would probably, with a higher probability, to steal energy from negatively refracting mode in favor of positive.
Okay.
But maybe.
Okay, cool. Thank you.
You're welcome.
Thank you. And then our next question is from RED. Go ahead.
Yeah, so I have a very naive question, which is like, so in the second part, you had this positive refractive index points which were more probable, and this negative things which were less probable, right?
Yeah.
So does this, can we extend this idea to polaritons, where we have a large number of dark states and less dark modes and less number of bright modes, but somehow only the bright modes only contribute and the contribution from the dark modes die out, like here the contribution from the positive refractive index die out?
Maybe. The best answer which I have, maybe. I don't see how this can be implemented immediately, right? But indeed, what matters is that you need to rely on the properties of the medium. If you have a particle with a negative dispersion, with a negative slope of the dispersion curve, it is a good sign. It negatively refracts, and if you can find a way to efficiently transfer the excitation into this mode and to eliminate everything else, then you probably can do it. Another thing is here, why I like this photonic crystallization. As I said, all the polytonic implementations from solid state physics, as far as I know, suffers from narrow window for negatively refracting modes. But I by any means do I want to say that it is impossible. Maybe.
Okay, thank you. Yeah, thank you.
Thank you. All right. And then sorry. And then I actually have a quick question about the first part of your talk.
Yep.
We were talking about the phase kicks with the vacancies, though. And
Yeah.
I think you had, it was 60% filling factor, if I remember correctly. And you had to choose that very complex looking electric field scheme. So does that depend on, or can that be used for any optical lattice with 60% of vacancies, or is that for that specific, say, lattice occupancy? First, like the certain atoms have to be in specific lattice sites.
Yeah, thanks for asking. I skipped it because I hoped that I will tell about the third part as well. So, in principle, in order to come up with the phasors, with the phase factors for each small square in this picture that would produce the localization, you need to know the disordered potential that you have here, right? To figure out which mask to put on each square, you basically need to know the disordered potential. So here it's just a simulation. So we kind of knew this potential and we were able to figure out with this. In practice, I think most of the measurements that are done with optical lattices are destructive. You basically release the optical lattice and measure the momentum distribution of the particles that are in there. So again, this technique, which was actually borrowed from optics of disordered media, where people just can make a few measurements and optimize the mask that they apply, is not very good for optical lattices. But again, as this whole bunch of ideas can be transferred onto another platform that is more stable, less disordered, and well, so it's more like a proof of principle, I think.
And then we have, oh, thank you. But we have another question from Johannes. Go ahead.
Hey, yeah, thanks. Very nice talk. I actually also wanted just to ask quickly about the first part. I mean, a very naive question. But I mean, all the focusing of this wave packet thing, you're talking about single excitation wave packet, quantum mechanics. But I mean, you get a very similar model if you just take sort of the hopping atoms in optical lattice, like a Bose-Hubbard model, for example. So what happens if you apply these focusing schemes to like superfluid states, so like to many-body states? Have you ever looked into this? Like what kind of could you prepare like focused superfluids, for example?
We did not look at that. It's a very good and valid point. Maybe. The best answer that I have, maybe. This is about a system where, when you can impose various phases site-wise. For each lattice site, you can impose its phase, and that's what you can do. And then you can apply these ideas to other systems, as you please.
It's just because I remember around this time, there was also a lot of interest in this stability of superfluids, for example, when you kick them with phases. And but I don't and they also did to do phase gradients and basically kicks, or you move the optical lattice. But I never remember people trying quadratic shifts or so. So maybe this would be.
Yeah, thanks for this question.
So you don't know about any work on this?
No, we did not make this connection. If you can send a reference, it would be nice, or just tell me what to look up, what are the keywords.
Thanks.
No. Okay. Then if we don't have any more questions, once again, thank you, Dr. Litinskaya. And then if you could allow me to share my screen, I will give the send off.
Thank you, and sorry for skipping the last part. It was the last year work, and probably, well, that happens.
Yeah. Well, I think, like you said, that's coming out soon, so I'll have to keep my eyes peeled out for that. Yeah, so we just want to remind you that we have, I believe, our third installment of our postdoc spotlight next week, featuring Dr. Silva and Dr. Liu. And thank you all for attending this meeting, and I hope to see you all next week. All right, thank you.
Thank you.